Hello friends, in the last video we learned about solving a second order homogeneous differential equation. Uh, so what were the steps? The steps were number one, find the auxiliary equation. That is step number one. We get the values of m if we have taken it to be m square plus am plus b is equal to 0, of course. So we'll get the values of m then. To determine what kind of case the value of m would be, whether it is your going to be real and distinct, whether it is going to be real and equal, and whether it is going to be complex in nature. So there are three types: your real and distinct, you have real and equal type of values of m, and you may also end up with a complex value of m. So the question is, then how do we solve? We knew, as I've told you in the last video, to very comprehensively sum it up, we know that y is equal to c1 y1 plus c2 y2. It is the solution general solution of any second order differential equation. Of course, it is only applicable for the homogeneous equations. Non-homogeneous equations have a different route to follow. They are in the some different form, which is y is equal to your yh of x and yp of x, where yh of x would be your complementary function and yp of x gives you a particular equation. Particular equation is the permanent equation, and your yh of x plus yp of x is the transient equation, right? So we'll talk more of that in later videos, but we'll first learn about the three cases what we had summarized. So for case 1, wherein roots are real and distinct, we have the value of y as a e to the power m1x plus b e to the power m2x. Now, if I ask you that you need to compare it with the general solution c1 y1 plus c2 y2, then what would you get? Here you obviously find that your c1 is equal to a, c2 is equal to b, your y1 is equal to e to the power m1x, y2 is equal to e to the power m2x. These are the values that you get on comparison with the standard general solution of a second order differential equation for real and distinct roots. So you get the two values, the value of y1 and y2. The basis of any second order differential equation is nothing but the set of the values, the two linearly independent values, y1 and your y2. So they are the two values that you will be getting on solving the equation, auxiliary equation. You get this value, you get this value. So your basis in this particular case would be y1 comma y2, which will be giving you your basis as e to the power m1x and e to the power m2x. So this is the case of the roots are real and distinct. For the case wherein your roots, case number 2, roots are equal. If your roots are equal, then you have the general solution as y is equal to a plus bx e to the alpha x if of course m1 is equal to m2 is equal to alpha. So expanding, we can find that a e to the alpha x plus b times x times e to the alpha x. So it is very easy to understand that this is your y1, x e to the alpha x then becomes your y2. So what is the basis then? Basis is y1 comma y2, which gives you e to the alpha x comma x e to the alpha x as the basis for this case, that is roots are equal. For the last and third case, that is case number 3, which is your case of complex roots for values of m. Herein, as we have discussed earlier, your standard differential equation in the form y is equal to e to the alpha x a cos beta x plus b sine beta x. So on direct expansion, we find that y is equal to a e to the alpha x cos beta x plus b e to the alpha x sine beta x. So find this. Now from here, very easy to judge again. This is your y1, this is your y2. Thus, basis of it is e to the alpha x cos beta x, and you have e to the alpha x sine beta x. So these are the two or the basis of the complex roots, right? We'll now come and learn about how to determine determination of linear independence or linear dependence. Linear independence we represent as Li, and we represent it as LD. Li, LD. So you have two methods, very easy. Either you can find, if you know the basis to be y1 and y2, this is the prerequisite. You know the basis as y1 and y2, and if y1 by y2 is some function of x, then it is safe for you to say that the function is Li, and if the value of it resembles some constant k, then it is safe for you to say it as linearly dependent. The second method, however, is a much more effective, but at the same time quite time consuming if you are slow, which is Wronskian method. So we'll learn about what the Wronskian method all is, and we'll find out the linear independence or dependence using the Wronskian method. So what is a Wronskian? Wronskian is always meant for two values. Here your y1 and y2 both are from basis. Both are from basis, and this equals the determinant of y1, y2, y1 dash, y2 dash, that is the derivatives. Now if Wronskian equal to 0, y1, y2 are linearly dependent. If Wronskian not equal to 0, y1 and y2 linearly dependent. So these are the criteria finding out the linear dependence and independence of the solution. So either you can go by your y1 by y2 is equal to fx, which is a very short root to it, or if it's a constant then it is a LD. If it is a function of some function of x that has been caught by the roadside, it is a Li function. And the Wronskian method in it basically is a determinant of the basis and the derivatives, and if that resultant value or the determinant is equal to 0, then it is safe to say that the two functions are linearly dependent. And if Wronskian of the two functions is not equal to 0, then it is safe to say that the two functions are linearly independent. So this was all about the basis, and we'll put a quick revision. So basis solutions, how to find out the auxiliary equation, the values of m. We put it and find out two values, and then we respectively put it in the place of the general solution. So case 1 wherein roots are real and distinct, for the value finding out the values of m, say m has two values, m1 and m2, right? So y in case of real and distinct roots is a e to the power m1x plus b e to the power m2x. So by comparison from this general solution, it is very easy to find out that y1 is equal to e to the power m1x and y2 is equal to e to the power m2x. So the basis would be your y1 and y2, which is e to the power m1x plus e to the power m2x. In the case that the roots are equal, y is equal to a plus bx e to the power alpha x, and if obviously taking into consideration the fact that m1 equal to m2 equal to alpha, then by comparison we get e to the alpha x as y1, e to the alpha x as y2. The basis then becomes the set of y1 and y2 values, which is nothing but e to the alpha x and x e to the alpha x. The third and last case wherein the complex roots exist and your standard equation is y is equal to e to the alpha x times a cos beta x plus b sin beta x. The general solution can be expanded and written in the form y is equal to a e to the alpha x cos beta x plus your b e to the alpha x sin beta x. So here y1 is equal to nothing but e to the alpha x cos beta x, and y2 is equal to e to the alpha x sin beta x. And thus as we have find out, we need to determine the linear independence or linear dependence of two functions. So if we know the basis from the given differential equation y1 and y2, we can find out the linear dependence or independence of the two functions very easily. You have two methods for that. One is the easiest of them all, which you definitely should try to apply, which is nothing but y1 divided by y2. If it's an animal, then if y1 and y2 is a function of x, then it is linearly independent, and if it's some constant k, then it is linearly dependent. Right. For Wronskian method, however, Wronskian, you need to find the determinant of the values, the basis or the values of the basis y1 and y2 and their derivatives. Correspondingly, you will get a value of Wronskian which will either be equal to 0 or not equal to 0. So if it's equal to 0, then you can say that the y1 and y2 are LD, and if it's not equal to 0, then you can find or say y1 and y2 are linearly independent. So that was it pretty much. So thank you again for watching. Do subscribe, and if any doubt exists, you can post it in the box below. Thank you and have a wonderful day.